This is a conversation with Ruth Kastner. She is a physicist and philosopher of science, popularly known for pioneering the possibilist transactional interpretation of quantum mechanics. She's also the author of 3 books: The Transactional Interpretation of Quantum Mechanics, Understanding Our Unseen Reality, and Adventures in Quantum Land. In this conversation, we discuss the decoupling of the philosophy of physics, the foundations of physics, from theoretical physics. We talk about the standard theory of quantum mechanics, the wave function, the measurement problem, Schrodinger's cat thought experiment, spacetime, realism, and then we spend the bulk of our time talking about the transactional interpretation. This is no time. If you like what you see, then do hit subscribe on YouTube, follow on Spotify, rate 5 stars on Apple Podcasts. This project takes a lot of my time, money, and effort. So if you'd like to see it continue, please consider making a donation on Patreon or Anchor. You can buy gifts on Instagram Reels. You can join as a member on YouTube, or you can buy super thanks. I'm starting to experiment with giving members early access to these interviews. So do consider supporting this project if you can. If not through monetary channels, then do consider sharing these episodes, leaving your likes and comments. All forms of engagement, they really go a long way. For other forms of love and support, you can follow this channel on Instagram or Twitter, or follow me personally. And now, it's no time. You were born into a family of physicists, and one day when your parents got a prism home, you were captivated by it. You thought it was magical. You were always captivated and enchanted by light and electromagnetism, and your love for physics blossomed from there. If you were in Plato's cave and your love for physics were the shadows that you saw on the walls, now as an adult, have you been able to turn back and look at the source of that love? Have you been able to dissect what it was about physics, about light, about electromagnetism that was so attractive to you at that young age?
Oh, well, thanks for that question. I do think to some extent, at this stage, I'm kind of at the stage where, we're in the cave and some very smart guys, some very smart people have come up with a theory that seems to work to predict what we're seeing on the walls of this cave. But I keep bugging, the other guys to say, hey, I think your theory might be pointing to something larger than this wall. If you look at the form of the theory that you have and you kind of take it in a realist way, then it seems like it's pointing to some larger realm, just by the structure of it. And so I keep bugging everyone to kind of turn around and hey, I think we might be seeing some indications from the theory that there's a source for these phenomena, and that what we've been thinking of this cave wall as our entire reality is worth expanding. That maybe we were wrong about that. So yeah, I'm kind of the troublemaker in the cave at this point, I think.
How did this start for you? Where does this love for physics, the love for philosophy, and this natural urge to be the troublemaker in this realm of physics, how did that start for you?
Well, I don't really know. I can just remember at a very young age, as you mentioned, of course, being enchanted by the sort of the hidden colors in the light that were revealed, that clearly they're there, and you just have to kind of subject them to the right sort of circumstance and the right kind of situation. They will show their hidden colors, and so that kind of exemplifies my sense that if we look in the right way, and if we're listening and kind of being receptive in the right way, that we're going to discover really cool, fascinating, hidden aspects to nature and to reality. So looking back, I can kind of just remember being out in nature and going, this is the play of light, that I'm seeing. What's behind that? What's the source of that? It's just always wanting to know, to get it's kind of a deeper understanding of the phenomena. So that's kind of been something that's underlaying, my different pursuits. And I did kind of have I've always enjoyed art and music. And so I, have a bit of what they call the checkerboard career, because when I first went to college, I actually studied studio art, and I was really into ceramics and the aesthetic beauty of these things. And then I ended up studying music because I had played violin for a long time. And, just one of the adolescent things where you're not sure what you want to do. But in the end, I just kind of got grabbed by physics again and went back to that. So there's just kind of that, I guess, kind of a determination on my part to find out what is really going on and not settle. I've never wanted to settle for sort of answers that kind of are FAP, the acronym that means for all practical purposes, that John Bell coined back in the 60s when he was annoyed with quantum theory and a kind of what he felt was hand waving around the problems of quantum theory. And so whenever I sense that there's kind of that move to kind of go, well, it works, I'm like, well, that's not good enough for me. I want to really understand what's going on. So that's just been the drive, I guess, that's been behind what I've been doing.
2 follow-up questions that I have for you from that. When you mentioned that you started off with arts and music, I think historically there's always been this divide between the science and the arts, where they're viewed as 2 completely mutually exclusive fields. Do you think there's an area of overlap between beauty in art and music that you can also apply in physics, that there's a role that creativity can play, that inspiration can play? Some researchers have actually spoken about the role of beauty in physics itself, and some have been criticized for it because they say that often physical models are not supposed to be beautiful and you shouldn't be chasing that as your objective outcome. Do you think there's a role for art, music, creativity, beauty in physics?
I do think there's a lot of overlap. Art and music and so on, the aesthetic realms are definitely part of the world. And, I don't buy into artificial boundaries. I think it's good. I think it's good for a particular discipline to maybe know, well, what is the limit of my ability? What is my domain of explanation? What is my proper domain of explanation? And actually, in that sense, I think sometimes physics actually goes a little too far, rather than say, oh, artists shouldn't be projecting onto physics, which, there's a legitimate question there. But I often see physicists kind of trying to use their discipline to explain away the human creativity and fields and so on. And that's kind of going the wrong way, the other way, where, no, I'm sorry, I come from a physics background and I love physics. But I think we also need to recognize, given the basic guidelines of physics and the basic kinds of assumptions that go into defining the discipline, don't tell me that you can tell me whether I have free will or not, or whether joy is real, or whether there's a God, or then you're just kind of overstepping. So I think physicists need to be a little more modest about the domain of explanation. And of course, I think wherever you can have a multidisciplinary approach that's responsible and sort of self-aware, that's good. I think that's constructive. I think that drawing the artificial boundaries, I think that's where we get into trouble, unnecessary trouble.
Yeah, I tend to agree. The second follow-up that I had for you was when you spoke about always wanting to ask the question why and getting to the root of the model of the system. Despite your love for physics and these questions that made you fall in love in physics in the first place, you've said in the previous interview that one of the toughest decisions of your life was making that switch from physics to philosophy. And honestly, when I discovered the existence of subjects like philosophy of physics or foundations of physics or philosophy of math, I was quite confused. It was surprising to me that rigorous fields like physics and math have decoupled and in a way outsourced, or so to speak, the foundational questions away from these fields into the philosophy departments. And theoretical physics seems to have adopted Niels Bohr's stance of you shouldn't ask where these questions come from. Like you shouldn't ask the source or the foundations, just shut up and calculate. And as a result, many academics, many professors who have come on the show as well have said that physics seems to have reached a standstill because it's running into these contradictions and paradoxes because it didn't solve the foundational questions, and now it's facing the repercussions. And math is also seeing the same problems with the paradoxes and the axioms. What do you make of this lay of the land with this decoupling of these foundational questions of physics into philosophy? And was that one of the big driving forces behind the decision to switch into the philosophy department?
Well, yeah, I think what you've described there is kind of, I think that's pretty accurate. It's a little unfortunate that we've had kind of this divide just kind of happen in a way. I don't think it was really planned, but I think that there was sort of a cultural move to, as you say, to kind of embrace Bohr's overall attitude of, there are certain questions physics shouldn't ask, which is, I think, a mistake. And I do have a paper that I wrote on, where I have a lot of sympathy for Bohr's predicament. So I don't want to be like, I'm going to trash Bohr. But I think he fell into an unfortunate stance as a result of certain, assumptions that he kind of carried with him. And again, this, in my view, deteriorated into a kind of a don't ask questions instrumentalism. And that became a kind of a cultural impulse that I think led to this divide that you describe. And of course, if you look back at the founders of quantum theory, Heisenberg, Einstein, Bohr, and at that time, and Planck, and these were guys who were very much concerned with philosophical grounding of physics. And as an aside, Einstein was a violinist, so he loved music, and I don't think just back to your previous, question, I don't think he thought of there being a divide between, aesthetic endeavors and physics. He would say things I want to know God's thoughts. So I think he was not one to make that, what I think, artificial division. And of course, physics in the very beginning, in its very beginnings, was called natural philosophy. So the divide is a kind of, that does describe the current situation. And of course, at the point where I, was studying physics, I did become aware of that, and that there was kind of, a bit of an instrumentalist kind of culture. And then I did become aware of the foundations of physics being done in the philosophy department. So I realized, well, this is, where my interests really lie. So at that point I said, well, I should just jump over there. And it was in the same university, so it wasn't that hard to do. And, worked with some really good people there, Jeff Boob, Alan Stairs, and got me up to speed on a lot of these issues. And, it's a very good experience there. So yeah. I'm glad I made that choice.
Yeah, I'm interested how this divide has been created and seems to be increasing, because classically, like way back in history, people like Aristotle, they were both philosophers and they used to study physics as well. All the way to even Galileo, Isaac Newton, all of them were also philosophers and physicists. And it's pretty much considered a similar, like the same field, but now it just seems to have branched out. And there seems to be this divide like you spoke about. Okay, let's start talking about some of these foundational questions to set the context and define the terms that we will use when we finally talk about the transactional interpretation later. In the book, The Character of Physical Law, Richard Feynman had said, there was a time when the newspapers said that only men understood the theory of relativity. I do not believe that there was ever such a time. On the other hand, I think it is safe to say that no one understands quantum mechanics. Do not keep saying to yourself, if you can possibly avoid it, but how can it be like that? Because you will get down the drain into a blind alley from which nobody has escaped. Let's see if we can prove Feynman wrong and get a few people to understand quantum mechanics and maybe even interested in them. Let's start with the most foundational question. What is the standard theory of quantum mechanics?
I guess it depends, like how to formulate the answer. Technically the standard or conventional theory is basically a couple of axioms in a way. It's a couple of postulates that kind of boil down to, the Schrodinger wave equation, which is just basically an equation that, describes how it attributes states to quantum systems. They're states that have certain mathematical character that are challenging in themselves, but we can get into that. But basically, a quantum system, say like a hydrogen atom, can be assigned what's called a quantum state. And then the Schrodinger equation describes how that state will change, will evolve as a function of a time parameter. And it's a deterministic evolution. So that's one of the, the basic axioms of quantum theory. And then the other one is sort of a postulate, and it has to do with so-called measurement. And it applies a rule to this quantum state called the Born rule, named after Max Born, who first formulated it. And basically it says, it's just a rule that says, okay, if I want to find out the probability that when I measure this system described by this state, say I want to find out what position it will be found in at some time t, then I will take my little quantum state that has been subject to the Schrodinger evolution, and I will take the absolute square of it. It's a mathematically complex object, and I will take what's called the absolute square, which is a way that you get a real quantity. You square it in such a way that you get a real value out of it that functions as a probability, a number between 0 and 1. And it will give you the probability that I will find this system at some particular value of x. So that's basically what it is. And it's clearly kind of an operational theory. Some people call it a principle theory. It's not a kind of theory that says, here's a model. It's not like what Maxwell and Boltzmann did back, a couple hundred years ago, where they developed a theory called the kinetic theory of gases, where they actually said, hey, I got some atoms and I'm going to model them and they're bouncing around and I'm going to describe their mechanics, how they're moving, and show you how you get other interesting things out of that. That's called a constructive theory. That's known as a constructive theory that kind of provides you a nuts and bolts model so you can hopefully get some insight into, what's going on. So quantum theory, in contrast, is not like that at all. It just assigns this kind of equation. It describes evolution of quantum states. And then it gives you this probability rule that you apply to those states. And it works at the level of these probabilities. So that's the conventional theory.
You'd be surprised how recently, even all the way to when I was in high school, all the way till year 10, we were taught that a hydrogen atom is classical in the sense that electrons are just orbiting the nucleus in these stable orbits. And then first day of grade 11 chemistry, they said, actually, that was a lie. None of that is true. And that's when I lost all trust with educational institutions. I felt very, very betrayed. You've introduced some really interesting ideas. You alluded to the wave function. So let's zoom in further into the wave function, the dream that stuff is made of. What is the wave function? Is it a physical entity of wave or some kind of a mathematical construct? And then you also brought a measurement. What is the measurement problem?
Okay. Well, first of all, this wave function is really, has gained a lot of significance, partly due to Schrodinger, because he is the one who sort of cast quantum theory in that form. But I should say that it was actually Heisenberg who, my understanding is Heisenberg was actually the first to get to the mathematical structure that underlies the theory. And his form of the theory was called matrix mechanics. And it has to do with a kind of a mathematical form that deals with matrices, which are basically arrays of numbers. And this was a bit esoteric. And in fact, when Heisenberg obtained this, he didn't even actually know what matrices were. He was just working with, how do I get this data to kind of give me something that seems to be empirically valid? And Schrodinger didn't like that. So he wanted something that seemed more physical. So he did something with Heisenberg's matrix mechanics that kind of dealt with a very special case of it. in terms of positions. So when you look at this matrix mechanics and you say, I'm going to prefer to know like where my system might be located, then you're dealing with positions. And that's what Schrodinger did. And when he did that, what happened is you have to project the quantum states. This sounds a little esoteric, but just let it wash over you if it doesn't make any sense. You have to do a mathematical procedure in which you take a quantum state and you project it into what's called the position basis. So you kind of take this quantum state and say, what is its relation to all the possible positions my system could be located? And when you do that, you get what's called the wave function. But it's a kind of a construct. It's technically called a probability amplitude. So to be completely accurate, you can get a probability amplitude for any kind of what's called observable, something you might want to measure. You can get a probability amplitude for the momentum of a system, or the energy of a system, or the kind of spin that a system is engaging in. So these so-called waves are actually probability amplitudes. And that's why you have to square them to get a probability. They kind of underlie the probabilities. So they have wave-like properties. And I do think, in terms of like, are these waves real? Well, they're not like water waves. They have important mathematical differences from things like classical water waves and sound waves and things like that. So they are not classical in that sense. But I take them as real in the sense that they are referring to something in the world. So in other words, I guess I have kind of a middle way. Like I wouldn't say, I wouldn't say, oh, the wave function is this, magical wave of consciousness. And it's like, no, I don't. I think that's starting to get a little bit too whimsical and not philosophically responsible, because technically at the relativistic level, wave functions don't exist, not for position. So it's an idealized notion that has physical content, but it does not have the kind of content that it's not like a water wave, and it's not something we want to kind of identify with nature at all levels, because again, it doesn't necessarily apply to nature at all levels, depending on what observable you're dealing with. But what I suggest is that it is revealing the structure of a domain of possibility that is real, that is really there. In other words, this is referring to something in nature. So whether or not this is observable, and no, it is not directly observable, but these probability amplitudes are, I argue, they're physically efficacious because they really are describing something about nature. So, and I think the second part of your question was, so then when we talk about measurement, the second sort of axiom of quantum theory involving the Born rule, the problem with the conventional theory is that it cannot tell you what counts as a measurement. So, measurement is kind of a term that has a lot of different shades of meaning. And of course, one of the shades of meaning is, kind of anthropomorphic, like, oh, I want to find something out, so I'm going to go measure it. And we do that. But the problem with the conventional theory is that it cannot actually tell you what it is about what you're doing that gives you an outcome, the outcome that you observe. So all it can do is tell you about correlations. All the conventional theory can do is tell you, well, you say you made a measurement, well, you correlated, you had your system, say an atom, undergo some kind of force-based correlation with what you're calling a pointer, which is some other system, okay, that you're going to correlate with your system of interest. And the conventional theory can only give you correlations. And so that's why we get this situation illustrated by the Schrodinger's cat paradox, which is, again, Schrodinger kind of recognizing this problem and illustrating it in what he meant to be a reductio ad absurdum, which means a demonstration that there's something wrong, with the theory. And so he illustrated this idea with, take some kind of atom that's going to send off some kind of a particle, and you want to find out when it's going to send off that particle. So you put in a Geiger counter, which detects the particle that it sends off. But all the conventional theory can do is tell you, well, I correlated my Geiger counter as a pointer, with my system. It can't tell you, okay, why at time t you actually saw something. It cannot tell you that. And so he kind of said, oh, well, that means I could hook up these other objects, like in his scenario, he's going to bring in a vial of poison gas and have that correlate with this atom. And then he's going to bring in a cat and correlate that with this poison gas. And no matter what you do, you never actually get an outcome at any particular time t. The theory just says, well, I'm going to get a probability that this will happen, but it can't tell you, why you even got that probability. Because all it actually gives you is this wave function that has these two different branches of, decayed atom and undecayed atom. And so dead cat and alive cat. And it doesn't actually give you the probability. You just have to impose that in an ad hoc way on your wave function. So that's the problem with the conventional theory. And the fashion lately has been to kind of shrug that off and go, well, it's not really a problem. It works it out. But actually, it is really a problem. And we have the fact that it is really a problem has been brought out in the past, actually pretty recently, 5 years or so, where a couple authors, Schrodinger and Renner, really made use of this idea and showed that you can have like nested observers. Like if you replace the cat in the box, with the box with the atom, with an experimenter, with a person, then you've got the situation where you've got another person outside the box who supposedly has to describe the person in the box by this grand superposition. And if that's what the conventional theory says, and that's what it says, when you do that, you actually get real inconsistencies. These are fatal inconsistencies that could be empirically observed. And what we've seen happen is people are kind of running away from that. They're running away from this Schrodinger-Renner scenario. They're saying things like, well, the two observers could never compare the results, so it would never be an outright inconsistency. That's not true. I have a couple people besides me have a published work showing that they could be compared. So you would get an outright inconsistency. So this is really a very, very serious problem for the conventional theory. And what we see is people trying to kind of get around it, and either they're trying to get around it and not really succeeding, or they're pretending like it's not a problem.
So there's two powerful ideas that you brought up. I just want to quickly summarize because this will be important when we start talking about the transactional interpretation. You spoke about the wave function, of it being this form of mathematical construct. It's made up of complex numbers. You square it to remove the imaginary part, and that gives you this one real prediction. And then you brought up Schrodinger's cat, which I love because it really helps laymen like me understand the absurdity of the standard theory. Because like you said, until the point of measurement, the cat is said to be in the superposition of both being dead and alive. You brought up the observer, you brought up the observer's friend, Wigner's friend as well. And at what point, does that superposition collapse? Is the observer also observing a dead cat and a live cat at the same time? Is the friend also observing the observer? It's quite absurd to me for sure. Two more definitions that we'll get through, and then we go into TI. Realism. What is realism?
Okay, well, realism is generally, it has a lot of different levels or different flavors of realism. I guess when I say that I'm a realist, what I mean is that I'm realist about quantum theory. And what we mean by that is that I think that the theory is referring to something in the world, something that exists in the world. So I take the theory as, describing something going on in the world. So that's what it means to be realist about a theory or to approach a theory from a stance of realism. that there's an ontological referent, the word referent meaning, what the theory is pointing to. So that, if an example would be the referent of Newton's theory of gravitation is a massive object or one or more massive objects, that is what it's describing, and they really exist. And it's easy for us to be realist about Newton's theory, because okay, it's not too hard to imagine that, yes, there are really masses out there, and that's what the theory is describing. So the opposite of realism about a theory, is called anti-realism, and that takes many forms. In terms of quantum theory or a particular scientific theory, when you take an anti-realist stance about it, what you're doing is making the theory about what I know or what the user of the theory knows. You're making it observer dependent. So you're saying the theory is not referring to something in the world. No, the theory is referring to my knowledge. So that it makes it it sort of denies that there's a referent of the theory in the world that the theory is describing. And instead, it says that the theory is basically an instrument that I use to increase my knowledge. Of course, in my mind, that kind of begs the question: well, what do you know if what's in your mind doesn't reflect what's in the world? Then what is it? What's going on in your mind? Why should we care? But anyway, that's kind of the rough definition and the contrast between realism and anti-realism. And they take many different forms. And, it also depends on whether you're talking about an ontological stance about the world itself. Then there's slightly different subtleties about the meaning of these words. But in terms of quantum theory, the anti-realist trend is to say that the theory is an instrument for me or the experimenter or the observer to gain knowledge, and end of story. And that there's a kind of I don't want to be too harsh here, but there's a bit of a preachiness that goes along with that. And in fact, some folks who adopt this view actually call their interpretations normative, meaning we want to make a norm, we want to provide guidance about the right way to do things. And that is to say that the theory is about my knowledge and my experiences. So they kind of really, in a sense, get a bit, it seems like a form of not being very humble about your interpretations. Like, it's fine to have that as an interpretation if you say, I can't make sense of the theory, so I'm just going to say it's an instrument. But everyone else, and they point the finger, that to me is like, no, thank you.
If I can attempt to summarize this with a popular riddle, if a tree falls in a forest and no one is around to hear it, doesn't make a sound, the realist would say that's observer independent. The event occurs regardless of if anyone's around. Whereas the anti-realist would say that no, it's observer dependent, that nothing else exists outside of your perception. Like the Irish philosopher George Berkeley used to say, to be is to perceive. Let's get the final definition out of the way. Spacetime. What is spacetime?
Yeah. So spacetime, in the way that I have been learning about it, turns out that in many respects, Einstein was right when he described spacetime as what he called a set of point coincidences, by which he kind of meant events. It's a set of events. So the that kind of gets into some technical issues, perhaps, about what is this set and what do we really mean by that. But to kind of maybe a negative definition will serve as a better starting point, and that is that what we think of when we use the word space-time. We think of, and we are taught to think of it as kind of a background or container for everything physically real in the universe. And that is kind of a background metaphysical assumption that underlies a lot of theorizing. So what I've been doing is questioning that and just kind of suggesting that quantum theory, in a sense, requires us to reevaluate that, which I think is more of a folk belief than something that it can really be considered valid. But that it boils down to we look around and we think that we see objects in space-time, in kind of a space-time container. So that is, in fact, not what space-time is. So it's really, strictly speaking, and we can get into a little more detail later, but in my proposal, what we call space-time is, or what the space-time that is actually described by relativity is the set of what we can call measurement outcomes, is a set of actualized events that I've kind of used the iceberg metaphor. So in this picture, space-time is really just the tip of the iceberg, the part that is observable, empirically evident, and that we can corroborate. And then, but there's much more to this iceberg. The submerged portion is this quantum level that you can think of as a realm of possibility, and that is real. So in other words, this quantum level is not part of the space-time construct, yet it is physically real.
We have all the ammo we need. I really appreciate you for taking this extra time to get me up to speed. I think we can now start committing sacrilege in Niels Bohr's eyes by asking what lies underneath all of this. What's the source of the wave function? What's underneath the tip of the iceberg? All the questions that he said we shouldn't ask. In 1986, John Cramer published the seminal paper, The Transactional Interpretation of Quantum Mechanics, where he, inspired by Richard Feynman and John Wheeler's absorber theory, he proposed a similar handshake or a transaction in quantum mechanics. So let's define all of these terms, this lingo that I've just thrown around, in light of everything we just spoke about, the standard theory wave function, the measurement problem. What is the transactional interpretation?
Okay, well, the first place to start, I guess, is to kind of go back to that quantum state, the idea of a quantum state, which can be represented by a wave function, if we're considering position, that basically, when we think about wave equations, technically wave equations have two different kinds of solutions. They have a solution that is kind of the standard ordinary one that is future directed, where the time parameter increases, so to speak. But there's also a solution equally mathematically valid called an advanced solution. And this is a solution that seems to indicate a wave progressing to smaller temporal values. In other words, a past-directed wave. So, of course, it's a matter of interpretation, what these waves really are. Are they really propagating? How are they propagating, and so on. Now, from Cramer's development and the way Cramer first looked into this, he comes from the tradition that, again, that space-time is the container for everything real. So he just assumed, okay, these wave equations that describe these quantum waves have the future-directed, so-called retarded solutions, and they also have these past-directed advanced solutions. Well, I'm going to use both of them, and if I do that, and sort of the inspiration for this, again, was, as you mentioned, the Wheeler-Feynman so-called absorber theory of radiation. And he said, if I do that, it turns out that when I look at the amplitude of this interaction between this forward propagating wave and this backward propagating wave, it actually gives me this squaring of the Born rule. It actually just falls right out when I look at that interaction and I see, what is the amplitude. And as he thought of it, it was kind of a circuit where what he called an offer wave, which was the retarded future directed wave, goes to an absorber, and that the absorber responds with what he called a confirmation wave, which was this advanced solution, heading so-called, as he saw it, backward in time, back to the emitter, that this circuit just seems to give you the Born rule. So that's actually what got my attention when I thought, oh, look, there's actually some sort of theory that can derive or provide some sort of derivation for this Born rule, which was just an ad hoc rule historically. And so Kramer called this the transactional interpretation of quantum theory. And, he argued that it gave you a basis for measurement, which I think was correct for basically the non-relativistic form that he was considering at that time, that there's a validity to the idea that it's actually this absorber response that is giving you the mathematical apparatus that you need in order to see where the Born rule comes from. So that's what kind of grabbed me. And I thought, well, this is worth exploring. So, the more fundamental way to think about this perhaps is that rather than just an interpretation of the conventional theory, the so-called transactional interpretation is really a subtly different theory because it works with a different theory of the way fields behave. So in other words, according to this theory, you don't simply have an emitter emitting what's called a retarded field, as people kind of tend to naturally think. But in fact, instead, radiation is a mutual process that involves the sort of ongoing participation of what we call absorbers, which are nothing more than, atoms that can, that are in, say, a lower energy state, such that they can jump up to some higher energy state if they receive this energy, it's radiation. So it's basically, the big difference here in this theory is that it has this mutuality. So that kind of in a nutshell is, the transactional interpretation, which actually I think I'm going to start calling transactional theory because it is a subtly different theory from the standard conventional theory. It does have a different model of the way the fields are behaving.
So just to check if I've understood this correctly, there are emitters and then there are absorbers, and we can talk about what emitters and absorbers are. And then there's this mutual, like you mentioned, this mutuality, this handshake or transaction between them. The emitter is emitting an offer wave to the absorber. There could be multiple absorbers. They could take in that offer wave, emit back. And I know I'm probably not using the right word when I say emit, but sending back, let's say, some form of a confirmation wave. You can have multiple of these possible transactions or handshakes. And in this entire range of spectrum of possible transactions, only one is actualized given by some probability. And that becomes the classical physical world that we see. Did I get that right?
That's pretty much it. Yeah. I would say that the emitters and absorbers are they're each actually generating a time symmetric field. Okay. So that's kind of the basic field interaction, that they are each generating a time symmetric field that has both these components, the retarded and advanced components. But the portion that goes back and forth between them from the standpoint of just looking at the kind of field that exists between those two, the emitter will be sending a retarded field that reaches the absorber, and then the emitter is receiving from the absorber this advanced field. And it's that overlap that creates that gives rise to this real energy. And as you said, you can have different possible, what I call incipient transactions. They are described by the Born rule. So you get the mathematical description of this field interaction precisely gives you all of that content that is in the so-called measurement transition that the standard theory just has to apply in an ad hoc way. So the standard theory has the mathematical apparatus that's going on in a so-called measurement, but it doesn't know where it came from. It can't provide any, justification for it.
Just want to take a quick digression because you brought up time symmetric fields. I think this is very important. So what are time symmetric fields? Does this imply retro causality? Does this imply going back in time, which many people consider is a problem?
Right. Well, and, at a technical level, a time symmetric field is a kind of a standard entity in, say, quantum field theory. It's one kind of what you call propagator. It's one way of answering the question, what kinds of energy are being propagated and in what temporal direction. And so these are all kind of mathematical entities. And then a question becomes, how physical are they, right? So these are mathematical entities that are all they're standard equipment in say, quantum field theory. But a so-called time symmetric field is simply, to be precise, at the quantum relativistic level, you have a field propagating, you have positive energies propagating in both negative and positive temporal directions. And you've got, did I say positive? Okay, positive energies propagating basically in both temporal directions. And you've got negative energies propagating in both temporal directions. So you basically have a field solution that just tells you, yeah, all forms of energy are going in all possible temporal directions. And that's a well-defined mathematical quantity. Then it becomes a question of, well, what, are you crazy? How can that be physically real? Okay. And this is where people end up making ad hoc choices based on their metaphysical beliefs and assumptions that, okay, I'm going to take out my pruning shears here now, which is what Feynman did. I'm going to prune off. I'm going to take the negative energies propagating in the positive direction and snip those off. And I'm going to take the positive energies propagating in the negative direction and snip those off. And we're going to have the Feynman propagator, yay. And it's going to describe what I think nature should be doing. And so that's what everyone uses. And it kind of works. I mean, Feynman was a smart guy and he deserved his Nobel Prize. However, what that process kind of foreclosed, arguably, this transactional picture. So if you impose on nature that everything's going in one temporal direction because causality, it turns out that you end up with weird problems like the measurement problem. So the remedy for that is to keep those time symmetric solutions and say, maybe nature is actually doing this, but not literally. In other words, it's not literally zipping around in space-time. Okay, so this is where we make use of our under the water submerged portion of the iceberg. We're at the level of possibility where hey, nature can maybe do stuff that you didn't think it could, like have what we might call virtual or possible situations that are set up by our quantum systems, and they can't all be actualized. And only say one of every given kind of measurement interaction, only one of those possibilities is going to be actualized. But when it is, the process of actualization breaks this time symmetry, this underlying quantum level time symmetry. It breaks the time symmetry. And then when you get your actualized events, observable events, they are behaving in a causal way. So we do retain causal, the kinds of causal phenomena that we see at the observable level. So that's kind of the lesson here is that, time symmetry, a lot of people are allergic to it because they want to say, I'm going to forbid nature from doing that because I don't see that happening. And see, that's where they go wrong. Just because you don't see it happening doesn't mean it's not happening. So it's a very fruitful way to proceed if we don't impose our constraints on nature.
I will revisit this feature of time symmetry and what people have considered that it implies retrocausality and the problem of causal loops when we start talking about some of the criticisms of this interpretation. So we will come back to it. I'll park it because I'm going to continue fleshing out the theory. So you mentioned that the natural question to ask would be about all these different entities, how physical are they, right? So I want to ask that same question about all these entities you've introduced, the absorbers, the emitters, the offer waves, and the confirmation waves. Are these physical entities? Are these mathematical constructs? How do we think of them?
Well, yes, they are physically real. In other words, I'm being realist about the mathematical objects that, that seem to work very well. And I argue they work well because they're describing something nature's doing. It's a simple, it's just a simple abductive inference is what we call it. Inference to the best explanation. So I do view them as physically real. And this is, again, where I break with that traditional idea that if it's not a space-time object, it can't be physically real. So what I say is, okay, well, nature's just bigger than you thought. And we have to understand these entities and processes as really in the world. They're just not in that empirically observable portion, tip of the iceberg portion of the world.
In a way, these are abstractions of that deeper, unseen quantum land, and we just get to see some projection of it in this actualized world that we know.
Yeah, and I mean, I would say, I'm not sure, sometimes the word abstract can be used to deny that things are physically real.
Right.
So, I mean, what we can say is a theory in itself can be thought of an abstract entity, a kind of a map. So in that sense, yeah, the mathematical objects are pointers to something real. They are kind of indicators. They are representation of something that happens in nature. And again, yeah, that doesn't mean that they describe all that's going on. They are describing a certain aspect of what is going on that will eventually correspond to something that we can observe.
So we have introduced the entities, we have introduced the characters and established relationships with each other. Let's bring it back to the measurement problem. So how does this theory solve the measurement problem?
Well, what it does is it replaces this vague notion of observer with a specific physical interaction and object. You could say absorbers, but these are all just atoms again. So when we say emitters and absorbers, we really simply mean ordinary physical systems like a hydrogen atom. So for instance, take a hydrogen atom that's in an excited state. It's got a little extra energy in it. It means the electron is not in its lowest energy state. And these are actually a little bit unstable, these excited states. So this is our typical emitter. And then our typical absorber is say, an atom in a ground state. So when you have the situation where these atoms and the charged particles that are parts of the atoms, the electrons and so on, according to this direct action theory, this absorber theory, they are always connected by this time symmetric propagator. So they always kind of know, and that's what it really means for an object to have charge, is that it's constantly in a connection with these other charged objects. So they kind of have this connection allows them to have the potentiality for interacting in a higher level way in a transaction, which consists of the emitter generating this time symmetric field that propagates to various absorbers, potential absorbers. They respond, and it's merely more of a mutual process at the relativistic level. It's not like one happens before the other. It's a mutual interaction. So they're each generating a time symmetric field that has the kind of a phase relationship that results in this symmetry breaking, where you get a collapse. So you get real collapse. This is technically called a non-unitary process. So when this happens, when you get this mutual interaction where they each generate their time symmetric field, and you get an effective offer wave and the conformations from the absorbers, this is the breaking of that linear Schrodinger evolution. So this breaks that evolution naturally by reference to a specific physical interaction. And you get collapse, you get real collapse, and you get a real outcome, which is a photon going from the emitter to one of these absorbers, the one that sort of won the actualized transaction. And that's all a measurement is. It's actually, measurements are always carried out through photon exchanges. And so the key here is you get real physical non-unitarity. And you get it not by tinkering with the Schrodinger equation, which, sometimes people think, oh, this is a spontaneous collapse interpretation. And that means it's not really quantum theory, and she had to tinker with it to, No, and nobody's tinkering with anything. We're simply saying if nature's behaving according to this direct action theory of fields, the fields themselves will do this, will break that unitary, that kind of unbroken evolution that seems to give you Schrodinger's cat will actually get broken at a very basic level between that, going back to Schrodinger's cat scenario, we'll actually you'll get a well-defined probability at any particular time that if someone were to open the box, that basically the Geiger counter would be triggered. And because there are so many, you can actually quantitatively show that the more emitters and absorbers that you have, the larger your system is, the more likely this kind of collapse is to occur, and this faster it will occur at a smaller microscopic level. So you don't get these macroscopic superpositions happening. You just, it naturally break down. So that's how it solves the measurement problem, by getting rid of this ill-defined notion of observer, because you can never define what you mean by observer, and saying, no, there's a physical interaction that happens among these systems.
I just want to clarify that last aspect about the macroscopic observer. So let's bring back the Schrodinger's cat thought experiment. I think I only understand tough ideas if cats are involved. So let's bring that setup back. There's the radioactive atom. There's the vial with poisonous gas. There's the cat. There's the observer. And there's the observer's friend, Wigner's friend. As you go from the radioactive atom to this macroscopic cat to the observer to the observer's friend, how many of these are quantum states? How many of these exist as a superposition? And then in this train of quantum states, how do you decide at what point to make the cut? What's in a quantum state and what's not?
Well, the cut happens naturally because based on how many degrees of freedom are involved in your setup. So in the case of an unstable atom, and take that unstable atom and a Geiger counter, the Geiger counter is already an overwhelmingly humongous collection of absorbers. And with that many absorbers, you can actually calculate. I have a paper for people who want the hardcore, nitty gritty. You can actually calculate what is the probability at any particular time that you're going to get a non-unitary interaction. And once you get to systems that, if you even get to like a human hair, then you're overwhelmingly likely to get a collapse kind of interaction, a transaction in a tiny amount of time. So the quantum state, you can describe anything you want by a quantum state. The point is, did you have a unitary process, a non-unitary process or not? And you can calculate the probability that you're going to have that. This kind of a subtler level of we not only have the probability of a particular outcome, we actually also have the probability that you will have a transaction. It's a time-dependent probability, and you can calculate it specifically for any system that you have, but you have to take into account how many absorbers are involved, what are the states that those absorbers will be transitioning between, and so on. You have to put in all those details. And when you do that, for instance, you get, like, if you do that with buckyballs, which are these large carbon molecules, they're kind of mesoscopic. And if you run a two-slit experiment with buckyballs, which people have done, you can get some degree of interference, but you also get a lot of collapse happening because the interference is getting washed out. Why? Because these are large enough objects that the transactional process is about 50% likely to happen. You can actually calculate how likely is it that you're going to get collapse in that, and that predicts perfectly, the kinds of phenomena you see when you work with buckyballs. So that's basically it. Is that you get transactions happening. You can't know. You only have probabilities. You can't say for sure at what time a transaction will occur. And that is also according to the uncertainty principle that won't let you do that. But you can get a very well-defined probability such that, it's overwhelmingly, like, the chance that you could get a Geiger counter in a superposition, the chances physically that superposition would persist up to the point where someone opened the box would be like 0.00001, that it's so tiny, it's not zero, but it's so tiny that, you're never going to see it. So you get these well-defined quantitative probabilities for at what point in your experiment collapse is going to happen.
In John Kramer's original take, you've mentioned that he considers space-time a container for everything real. And I believe in your extension of the theory, the possibilist transactional interpretation, and now the theory that you've developed, you've moved away from that idea and you're saying space-time is not this fundamental container, but it's this emergent construct from this deeper, unseen quantum land. Is that the biggest deviation that you have taken from the original theory, or are there other key features of your extension?
That's kind of a big interpretive deviation that I've taken from Kramer's proposal. The other extension, if you will, is that what I've done, I have elaborated the transactional picture into the relativistic domain explicitly. So not so much a deviation, but it's an elaboration. It fills in it answers a lot of questions that arose for the original non-relativistic Kramer version. So, for instance, people might go, well, where do these offer waves? Why does an offer wave happen? What's going on there? That's how I've laid that all out. And I mean, I mentioned some of it previously here, but basically, you can quantify all of these things in terms of what are called coupling amplitudes. And for all we mean by that, for the case of, say, electrons and their interaction with light, that's just the charge of the electron. So it turns out that the charge of the electron, it's also called its coupling amplitude. It couples to the electromagnetic field. That is the amplitude that electron, it's like a basic bare bones amplitude that electron will engage in a transaction. So that was kind of my innovation when I was going back and looking at quantum field theory. And in fact, Feynman had suggested that he had characterized the charge or the coupling amplitude as the amplitude to emit a photon or the amplitude to emit a real photon. So, and he was right about that, within the context of his interpretation. So what I did is I slightly reinterpreted it. And I said, within the context of the direct action theory, the charge of the electron is the amplitude to either emit or absorb a real photon, which really in the transactional picture means the amplitude to generate an offer wave or a confirmation wave. So it's in the charge, the coupling amplitude, that we get that basic birthplace of offers and confirmations. That's the basic amplitude that a charged particle will generate either an offer or confirmation. But you need other conditions too. You have to have energy conservation, and you also have to define what states would be involved were that to happen, where the offer wave would be a wave to go from this state to that state. So in other words, they have to be defined by these other parameters as well. But that's the basic. So that's the basic, I think, that was the missing link for me that enabled the full relativistic development of the theory, to recognize what these coupling amplitudes are and that they are the basic amplitude for emitting or an offer or confirmation wave. And that's why you need two factors of them, because you need both. In order to get a real photon, you need both the offer, the confirmation. That gives you two factors of the coupling amplitude, which is none other than the fine structure constant. The so-called fine structure constant is this fundamental constant in quantum electrodynamics that pops up all the time. So in the transactional formulation, you really see why you must always be dealing with the fine structure constant, because it's going to naturally come in whenever you have a transaction.
What's creating all the probabilities? Pierre Curie had put forward the Curie principle, where he had said a particular result, that is the choice of one outcome among many equally possible ones, requires a particular cause. It's not good enough to say that one of the possible outcomes just happens. One must be able to point to a specific reason for that outcome to occur, as opposed to all the others. I know that this has been ridiculed by John Buridan with the Buridan's ass paradox, but I do think there's some merit to Curie's principle that there has to be some source. Where do these probabilities come from? Einstein had famously said that God does not play dice. Do you think there's a deterministic process that lies underneath all of these probabilities? Can we go even one more layer deeper? Can we go below whatever's below the tip of the iceberg?
Well, that's a big topic. And I mean, it's sort of like, it's a different, there's one, there's the concern about what the Leibniz principle of sufficient reason, which is basically what Curie was talking about there. There's that natural desire to have some sufficient reason. But then there's also, well, where do these probabilities come from? I would say, I'm sorry, guys, they come from quantum theory. They just, that's their, no, don't just go to your room. So that's where they come from. So the question is, well, what do we make of them, and are they problems? Is it a problem or not? I mean, to go back a little bit, a natural way to understand these probabilities is, again, like, okay, nature's telling us that it's dealing with possibility. Possibility is real. The natural way to encode that in a theory, the natural theory you're going to get is going to tell you how likely these possibilities are, guys. So that's what you want. Don't say no to the probabilities. They're giving you, a nice quantitative characterization of possibilities that could really be there. So it's sort of a natural thing. It's not like some defect of the theory if one allows the idea that quantum theory is suggesting there are possibilities. Now to this issue of the desire for an explanation of why do I get one and not another one? Well, here I have to, that's a deep question, but before I get into it, I have to point out a double standard that pops up when people are posing this question, kind of as a criticism, say, of TI or of the basic idea that there's something missing here. Well, then I go, well, why then aren't you raising the same criticism for the Higgs mechanism? So it's part of the standard model that we have this so-called Higgs mechanism that is supposedly required to give mass to bosons like the weak bosons, the Z and W bosons. And that inevitably brings with it this whole continuum of possible ground states for nature that the theory will never tell you why one is chosen. And people are like fine with that. And they say spontaneous symmetry breaking. So this is kind of to get back at the meta social criticism cultural level, is to kind of ask these people, why does it seem like a problem for you that in quantum theory you have probabilities and the theory will not tell you which one gets actualized? But why is it not a problem for you that the Higgs mechanism gives you even more possibility, an infinity of possibilities, and it won't tell you which one nature's picking? So why don't you guys ask yourself that, for starters? So that's kind of, so the basic lesson here is that standard physics accepts the idea of spontaneous symmetry breaking. So, if I wanted to kind of, just the easiest way to kind of, do the tennis, hit back that serve of, oh, you didn't tell us why one outcome happened. It's that Higgs mechanism, spontaneous symmetry. That's the easiest, I'm like, it's not a valid criticism unless, now, if you guys want to get tied up in knots about the Higgs mechanism too, and you want to say, oh, I hate this. This is no good because the Higgs mechanism doesn't tell me why nature ends up in one of these ground states. Now, if they want to be consistent, okay, then we go, okay, well, what's the deal here? This is very puzzling. And you could say, well, it's puzzling. It seems to violate Leibniz's principle of sufficient reason. And it does seem to. Now, again, you could say, okay, spontaneous symmetry breaking. But if we want to push back on that, we want to say, well, I don't like that. Then you can actually investigate a benefit that comes from the genuine indeterminacy of the theory, where it's really not going to give you a mechanism, not going to give you a deterministic mechanism. You could say, oh, well, I have an opening for free will then. So, so it's not like this is necessarily bad. So when we want to make judgments about what counts as a good explanation, what is it that's missing? Is there something missing? We always have to look to ourselves and say, well, what are my background requirements for a good theory? What am I demanding of a theory? And when we do that, we find that, conventional physics, the usual demand is for a mechanistic deterministic explanation of everything. And in classical physics, that made sense for the world, the kind of phenomena we saw, and that certainly made sense. And you have physicists saying, Huygens and others saying, if we cannot provide a mechanical model of it, then we don't understand it. So that exemplifies that desire for that kind of understanding. And at this point, this is an opportunity for us to kind of step back and go, does nature really behave that way? If it doesn't, and in fact, there is some weird irreducible element of indeterminism. What do I get from that? What could that be a good thing? Could I get a source for volition in the world, a source for real, genuine novelty, real, genuine creativity? Where the price is, oh crap, I can't make a Tinker Toy model of it. Well, maybe it's worth, maybe this is when I talk about training wheels, that in a sense, maybe this causal deterministic kind of ideal for theories or is kind of like some training wheels that served us well, but maybe it's time to let go of those. And maybe nature isn't really like that.
I tend to agree that there is this selective dismissal of theories that don't follow this causal deterministic nature, and it's just being applied arbitrarily to some theories, whereas many of the theories in quantum mechanics as we know it do not have sufficient explanations, I guess. While you're hitting back tennis serves, then I should use this time to also ask you to hit back a few more tennis serves. I do want to cover some popular criticisms. Professor Tim Maudlin had raised some objections with TI, which you've said in the past were considered fatal by many researchers. In his book, Quantum Non-Locality and Relativity, I was able to find arguments for his inconsistency challenge. And we've already touched upon quite a few of this. We spoke about retrocausality, or the problem that he implied of going back in time causal loops. And we just covered the questions about how the probabilities arise, echoing the Curie principle. And he also asked a question about what really determines whether a transaction is actualized. I'm sure I'm not doing full justice to his stance, and I'm sure you know his criticisms better than me. So can you step into the shoes of some of the critics of TI and steelman their case? Can you objectively list out some of the limitations of TI if you had to criticize it? And then can you step back and hit those tennis serves back to them and respond to those criticisms?
Well, yeah, I haven't actually found any holes in the theory in terms of or contradictions or inconsistencies. So I haven't found those. I mean, whenever someone raises what they think is a concern or an inconsistency, I take it seriously and I explore it. And it just always seems to kind of like be a knot that when I go to, it's like it unravels and it ended up not really being a problem. So, I try to be, and as I've said, it's like I'm not a true believer about TI. I've been exploring it because I think it's fruitful. And if it really turned out to be crap, I have other interests. I could practice piano. I could do a lot more, I have other things I could do. I wouldn't need to waste time on it. But in fact, whenever I look at these, they always turn out to be this kind of like, well, this person is working with some assumptions that really don't hold. Like the space-time is a container thing, which is where you get into causal loop. This is not a thing going literally backward and forward in time. And that's inconsistent anyway for other reasons. So that I've written about. The whole Maudlin thing, the Maudlin's main objection was through what I call contingent absorber experiments, where he thought he had this sort of inconsistency that came out from this thought experiment where you only swing an absorber into place if one of the transactions doesn't get actualized and so on. Well, in fact, you can't even do this experiment if you truly are working with the real direct action picture at the relativistic level. What you find out is that you never have this so-called slow moving offer wave. That was the whole basis for his thought experiment. So it doesn't get off the ground. And I've laid that out in publications. So the objections just really don't hold up. And what I find people doing is kind of doing straw man objections where they're dealing with the 1986 version And Kramer had these narratives about pseudo time, and he thought things were literally going backward and forward in space time. And yeah, you get into trouble if that's what you're saying. But I'm not saying that, and you don't need any of that. So, and in fact, the power of letting go of that notion that everything's happening in space time is that you get a reconciliation of quantum theory with general relativity, which I've just demonstrated with a colleague of mine, Andreas Schlatter. And we have, it's not the traditional quantum theory of gravity because it doesn't treat gravity as a quantum field, but it unites the quantum level with the space-time level, and we derive the Einstein equations from this direct action picture. So it's very fruitful, and it's all fully consistent with relativity. It doesn't violate relativity in any way. So what I keep seeing is that, you know, these kinds of objections often come from double standards as well. For instance, Professor Maudlin, is an advocate of the de Broglie-Bohm pilot wave picture, and a question for that one, for one thing, that's not relativistically. It's hard to extend it to the relativistic domain. And it seems to require kind of a preferred coordinate system. And there are ways to kind of get around that. But the basic thing is to ask, how does the so-called pilot wave, which they say is a configuration space object, interact with the so-called corpuscle, which is the supposedly physical object? No one ever answers what's the physical interaction there? That's a big lacuna in the theory. They just take it like, well, I'm just going to say that. And they don't seem to perceive that they don't have a complete theory. They're just that this wave is supposed to push, a configuration space wave is supposed to push a particle around. So give me the account of that. So, that's kind of missing. And actually, the so-called Bohmian theory, he actually abandoned it about a decade after he proposed it. But it also has consistency problems with the Froschiger-Renner scenario as well, because it relies on this hidden variable of the corpuscle to assign an outcome state, but it still assumes that the unitarity is not broken. So you can have an outside observer that's going to deny that outcome state occurred. And then ultimately the inner observer should, according to this usual conventional approach, be making wrong predictions based on his state assignment. So he will have to say, no, my state assignment is wrong. When I find out that some outer observer knew that I was really in a superposition, I'm going to have to change my outcome state because it's wrong. So it has these consistency problems. So anyway, so that's hopefully answered that question.
You mentioned how this theory can bridge the gap between quantum theory and general relativity, which has been this big problem that has dominated physics for the last century. And there are other competing alternate theories. You mentioned one just now that other academics have proposed that also have the same ambition. And I do see some similarities. I see some similarities with twistor theory put forward by Sir Roger Penrose, Peter Voigt. In that theory as well, space-time is emergent from this higher dimensional, non-local twistor space. So there's at least that aspect that's similar. You mentioned there's a lacuna in Bohmian mechanics in the de Broglie-Bohm theory, but I did see very faint echoes in the pilot wave and these alpha waves and confirmation waves. Although after that point, I stopped seeing those echoes. Obviously, pilot wave theory is a lot more deterministic. And I do see a lot of similarities with Wolfram physics proposed by Stephen Wolfram, in which he has this entire universe of nodes very similar to observers and emitters. And then they have these connections between the nodes that are very similar to these handshakes and transactions. And there's a probability assigned to each connection between these nodes. And then there's the entire universe of possibilities, which he calls the Roolead. I'm curious whether you've studied any of these alternative theories in detail, and do you feel there's an area of overlap between any of these theories, if at all, or do you feel like they are direct conflict with TI?
Well, the latter theory, the twistor theory, I'm not I'm not real familiar with, but there is some overlap for theories that want to take seriously the idea of possibility. And, and I welcome that. I think that is kind of the more fruitful direction to go in, and to kind of take seriously the Hilbert space structure. This is a higher mathematical space that the quantum states are elements of this space. And I think the right move is to say, this is something that's going on in nature. So that, as the kind of structural realist part of me would say, yeah, I think you're getting at the right kind of structure to acknowledge the reality of possibility, which was the subtitle of one of my books. So there's overlap there. I guess the big difference between approaches like that and TI is that they're kind of formal constructs that are trying to kind of create an alternative map, if you will, from everyday experience that is also consistent with what we get from quantum theory and so on. It's kind of a formal construct, where TI is a specific physical model. It's not a formal construct. It deals with a theory of the way fields are behaving. So it's not, I'm not positing a node or, it's not a formal construct. I'm saying, look, physics is fine if they would just recognize, as I think, that nature is behaving according to the direct action theory, that's what's really going on in nature. And if we just take that into account and consistently incorporate that into the theories, we naturally get all this stuff. We get the Born rule. We get a reason for measurement. We get an emergent space-time, that naturally seems to come out where we get observable causality. So at the observable level, we get obedience with relativity theory. We get all the phenomena that we need. So it's not I'm not sort of striking out and saying, I'm going to create a new formal construct. It's a very simple remedy. And it's a nuts and bolts theory. It's saying, this is what's really going on. These atoms are mutually interacting at a fundamental level.
I think it's a very intriguing theory, and I'm very interested to see how it develops from here. Let's start wrapping up with the last three questions. What are some books, movies, role models that have strongly influenced you in your life?
I guess on a broader cultural level, well, my favorite movie so far is The Matrix.
Okay.
I mean, I love science fiction. I'm a Trekkie. I love Babylon 5. I adore science fiction. So that's kind of, the lowbrow aspect here. I love a lot of different kinds of music. I'm an amateur musician, and as I mentioned to you earlier, I've kind of dabbled in sacred vocal music. I sung with a group called Cantores in Ecclesia, who have the annual William Byrd Festival. And I actually, together with my sister, have written a screenplay about the life of William Byrd. He was a composer for Queen Elizabeth, and he was a devout Catholic, and she was, of course, threatened by Catholics, and so there was a lot of intrigue and conflict there. And he was very naughty and constantly, pushed the envelope and consorted with Jesuits, and she always kept him out of trouble. So it's a fascinating story. So he's kind of in the music realm. William Byrd, Thomas Tallis, Palestrina, they're very inspirational to me. I also love rock and roll. I love Led Zeppelin. I mean, old timer rock and roll person. I like to learn about other cultures. I'm a yoga instructor, so I'm familiar with Indian philosophy. Trying to think of other inspirations.
Book recommendations? Books,
because I read so much nonfiction, I mean, I don't read a lot of fiction. And again, I guess it would be, I used to love Arthur C. Clarke, The City and the Stars, when I was a kid. A very early science fiction book that really influenced me when I was in, what they used to call junior high school, was called The Star Seekers by Milton Lesser. And it's a very obscure great little science fiction story about some people in a rocket ship, the multi-generational rocket ship that was designed to be like a planet, and it had 4 layers, and they were sent out from Earth to find a new home, and along the way they forgot where they were from, and it's funny to see what happens. But they all go their separate ways and don't know what the Earth was and are unprepared for their destination. So I'm trying to think of any other inspirations. Yeah, I don't know.
Well, if it comes back to you, you can always email me.
Sure.
What would you like your legacy to be? How do you want to be remembered?
Somebody who was trying to figure out how nature's really working and not content to be satisfied with the FAP, hand wavy, oh, it's not really a problem, or, shut up and calculate, and just kept trying to be teachable. And, I think I've heard this, somebody quoted, I think it might have been Chris Fuchs, who said something like that the foundations of physics community is like a bunch of people who are like religious zealots, and and all they do is, when a new experiment comes out, they explain why their interpretation is the best. And I do not want to be that, So when someone said this to me, I was like, okay, well, count me out. I mean, I'm trying to be a good learner, a good student of nature. And if nature slaps me down and says, no, your little transactional thing is crap, then I will obey. And I am not a true believer. And of course, I like it. I think it works, but I really object to this idea that people, that it's like correct for people to be, religious zealots about their interpretation. I think that's kind of sad and tragic, and it shouldn't be that way. And so anyway, for my legacy, I don't know, I'm always a troublemaker. I don't mean to be. I just question authority. If someone gets dogmatic on you, just get back in their face, because no. Don't accept dogma from scientists. I mean, if the church comes at me, I'll be like, I get it. That's what you're about. But, this dogmatic stuff, no, thank you.
I love that you're a troublemaker. And just in preparing for this episode, all these interviews that I've watched of yours, the books I've read of yours, I think it's powerful what you're doing. And I must say, every time when you come across a new theory for these standard formulations of physics, it really unlocks a different way of thinking about things that I hadn't explored earlier. So for that reason, I think it's a rich idea, and I've already seen the benefits of just unlocking that gateway, which I'd never even thought of before, never even thought of the world or the nature of reality in that sense. Final question. This conversation has been witness to your in-depth explorations of the fabric of reality. And like you just mentioned, you have, along with your immense knowledge in physics, your varied interests. You had an interest in art, music. We spoke about that earlier. You have been very interested in many spiritual traditions. You're a certified yoga teacher. You've been very interested in Eastern philosophy, Indian philosophy. So I have to ask you, it's a crime if I don't ask you the ultimate philosophical question. What is the meaning of life, Ruth Kastner?
Well, I used to be a TM. I'm kind of a lapsed meditator, but I was in the TM movement for a while. And a related question is, someone asked Maharishi Mahesh Yogi, why is there many instead of the one? And he said, because there is no fun in loneliness. So I don't know. Are we here to have fun? I sure don't know. I mean, I think we're here to find out what's really going on behind the superficial, Maya, if you will. And I think what's really going on is immensely cooler than the mundane, mechanical looking phenomena of everyday life. And I think, when I meet people and when people who are really open to learning about nature, about what's really going on, they're having fun, and that's where the meaning is. There's beauty to be created in art, in music, in exchange of ideas, in hearing other people and in learning from other people. And I think there's real joy there. So I don't know, I'm not sure I could really pin down any meaning, but certainly getting to the opening of Plato's cave and the bright sunshine and seeing that there's a lot of beauty out there, I think that's probably very meaningful.
There is a Buddhist saying, if there was no illusion, there would be no enlightenment. So I really hope you get past the Maya, the illusion, and when you get to the bright sunshine, you let me know what you find. I like it. Professor, if people want to connect with you, if they want to find out more about you, read your books, find out more about TI, what is the best way to find you or your work?
Okay, well, I have a blog called transactionalinterpretation.org. And I also have an author page. It's just my full name. It's ruthekastner.org. Mm-hmm. And I'm on Facebook and a little bit I'm not so much on Twitter. I'm not going to use the new name. Not so much on that anymore for obvious reasons. I can be found on Blue Sky and on Mastodon. So I'm around and I'm always happy to hear from people. I don't always have as much time as I'd like to sometimes people send me material and I can't always read really long pieces, but I'm always interested in people's ideas. So
that's the way to find you. Professor, thank you so much for such a fantastic conversation.
Thank you. It's been a pleasure.